Electron affinity, in a way, is sort of the opposite of ionization energy, because here we're talking about a neutral atom gaining an electron. So electron affinity, often abbreviated EA, is the energy change when a neutral atom gains an electron. Electron affinity is usually negative, meaning it's exothermic, but it can be positive. So in terms of money, okay, so here I am, I'm an atom, and someone's going to give me an electron. Do they have to pay me to take the electron? When they wanted one of my electrons, they had to pay me. Like they're buying my stuff, right? Here they're going to give me stuff. In the real world, what happens? Then I give them money, right? So electron affinity is usually negative, meaning I'm paying for that electron that's coming into me. It can be positive. Some alkaline earth metals and all noble gases have positive electron affinities. Why would a noble gas have a positive electron affinity? Let's look at neon. Neon has 10 valence electrons. 10 electrons. What would happen to its electron configuration if it got an extra electron? It'd become like sodium. Is sodium cool? No. Sodium was trying to be like neon. Neon already has a really stable electron configuration with a full valence shell. If you're going to stick another electron on it, now it's going to have an unfilled valence shell and it's not going to be as stable. You're going to have to give it energy to make it do that. The trends in electron affinity are less regular than the other trends. For group 1, the electron affinity decreases. It becomes more positive as you go down the group. But other groups don't really show a trend. So it really only works for the first one. Usually it increases as you go across a period, becoming more negative. Group 5 has a lower electron affinity than we expect because that extra electron has to pair up, and that's not preferable. Groups 2A and 8A have very low electron affinities because adding those electrons, they go into a higher energy. The highest one in any period is the halogen. So what can we really say about that? That was a bunch of kind of conflicting statements. Something like a noble gas that already has a great electron configuration it's not going to want to lose electrons, it's not going to want to gain electrons either. You think about the halogens, though. What happens with fluorine if it gains an electron? Is that a good thing for fluorine? That's a good thing for fluorine, because then it gets the noble gas configuration. So that's going to be a good thing. There's not a great trend there, but you just kind of think about, well, do they want an electron or not? It's not very satisfying. So we look here. So these guys are all greater than 0, meaning that you have to put energy in to get it to take the electron. I have to pay you to take this. These are negative. The atom will pay you to take the electron, which is how it should be. And these guys also. Nitrogen is a little weird in terms of that. These guys do have negative electron affinities, but they're much smaller than the ones over here. It's just not a real satisfying trend. So we'll stop talking about it. We need to compare metals and nonmetals. These are their properties all kind of lined up here. And these are generalizations. Metals tend to be malleable and ductile. And what that means, malleable means that you can pound it into a sheet. If you take a piece of iron and pound on it with with a hammer, you can flatten it out. Nonmetals don't do that. And ductile means it can be pulled into a wire. So nonmetals are going to be brittle in the solid state. Metals are not. When you drop a piece of metal, it might dent, but it's not going to shatter, right? Nonmetals are more likely to shatter. Metals are shiny, lustrous, they reflect light generally. Nonmetals not so much. Metals conduct heat and electricity. Nonmetals not so much. The oxides of metals are generally basic, they're ionic. The oxides of nonmetals are acidic and they're molecular. Metals form cations, nonmetals form anions and polyatomic ions. Metals lose electrons in reactions, loss of electrons. Oxidation is loss of electrons. Reduction is gain. Nonmetals tend to gain. So they really are kind of opposites. So when we talk about metallic character, it's like we've got this ideal metal, and he's got all these qualifications, kind of like the ideal guy, the ideal man. And so metallic characters, we're seeing, well, how closely do this element's properties line up with the ideal of a metal? How metallic is he? How macho is this guy, right? How much of a man is he? So metallic character decreases from left to right across the period. Okay, this makes sense to me, because if you look at the periodic table, and you look at, say, period 3, on the left we have sodium, magnesium, aluminum, those are metals, right? And on the right we have sulfur and chlorine and argon, those are nonmetals. What's happening with metallic character? It's decreasing as we go across. Metallic character increases as we go down a column. Nonmetals are found at the top of the middle main group, and not metals at the bottom. So if we look at, let's say, group 5A, nitrogen, phosphorus are at the top. They're nonmetals. As we go down, metallic character increases. We go through a couple of semi-metals, and we get to bismuth at the bottom that's a metal. So, trend in metallic character. So this is kind of a gee whiz illustration. Here we've got sodium. Here's a picture of sodium. Sodium is a very soft metal, but it is very metallic. It's got, it's shiny, and it's very ductile and malleable. And here's magnesium. And as we go across, metallic character decreases. Chlorine's a gas at room temperature. It's very non-metallic. And if we look at these guys, here we've got nitrogen's a gas, phosphorus is a solid, here we've got a couple of semi-metals, and now bismuth is starting to look a little more metallic, and so metallic character is increasing. So this one really is just kind of a no-brainer. I'm not sure why I've got so many slides about it, but here's that stair-step line separating the metals and the nonmetals. So if you're going across, oh, these are the nonmetals, these are the metals. The trend must be that it goes down in metallic character. Okay, on the basis of periodic trends, choose the more metallic element from each pair if possible. Germanium and tin. Tin is more metallic. These are in the same group, and tin is below. Gallium or tin. So here's gallium, and here's tin. As we go across this way, metallic character decreases. But as we go down this way, metallic character increases. These are opposing trends, aren't they? So we're going to say not possible to tell. How about phosphorus and bismuth, which is more metallic? Bismuth, because it's at the bottom of that period, a group. Bottom of the group. Questions?